Welcome to the third lecture of the module Robot Statics. This is about kinetostatic measures for robot design. In this lecture, I will be discussing kinetostatic measures, general derivation of force and velocity ellipsoids, and manipulability measures. So, let me just give you a small brief how we work actually, how humans work. First, if at all you are cycling, what you have felt, if this is a pedal, okay, so at a particular position over here, you see whenever you start the cycle, you start keeping your pedal something like this, so that you can apply maximum force. Okay, you cannot put it like this. In this case, if you apply force, it can go either here or here, and at the same time you won't be able to apply maximum force along this direction. Okay, whereas when you want to make it go fast, you keep the pedal like this, so that you can make it go in the maximum velocity. Okay, so at the tip over here and here, you want more velocity. Why? You don't want to get stuck at top dead or bottom dead centers, and this is the place where you can apply maximum force, and this is the place where you need more velocity and your legs are fully extended. Your legs are fully extended, legs are fully almost bent over here, and this is the mid range where you want to work, and this is the region is you can carry maximum amount of force. Okay, so that is cycling. Okay, so maximum velocity is in fully stressed condition, horizontal direction. Maximum force is, so that is in vertical direction. So you have two cases, maximum velocity and maximum forces. Okay, and in the second case, lifting a weight, you don't lift your weight keeping your arm fully stressed. Okay, you don't prefer doing work most of the time keeping your arm fully stretched. Why? You can carry less amount of load, so you want to remain somewhere in the middle. Okay, and while moving a jug, doing any household task, what you do, you normally be in the mid range. Okay, you don't fully stretched. Okay, so this is what is about force. When we try to lift any weight, you want to keep mostly during the mid range. So let's say you want to throw a cricket ball. What do? You normally stretch your arm to the maximum and throw the ball, so that you can impart a maximum velocity, impart the maximum velocity to the ball. Okay, but at the same time, when you play cricket, what you do? You keep the bat holding from both the arms, you keep the bat in the mid range and try to maneuver the bat, so that you can apply maximum force. So these are the few instances when you have noticed the configuration of your arm affects a lot how much is the maximum force that you can apply and what is the velocity that you can give. Okay, so with this as a background, let us begin. What is dexterous robot? Dexterous robot is the ability of the arm to reach all points within the workspace with all possible orientation of its end effector. So you reach somewhere, you can orient anyway, you can do whatever you can do over here or anywhere else. Okay, and can transmit motion and force comfortably. Okay, so at any location you can transmit motion, you can apply the forces in all the direction. Okay, it is not that as in case of fully stressed condition, you cannot push it further, but you can go only in vertical direction. So if your arm is fully stressed, you cannot go further along this direction, but you can move like this. Okay, okay, so dexterity is the measure of that. Dexterity WD and manipulability WM are quantifiable value for this. So WD is determinant of Jacobian and Wm is JJ transpose, that makes it a square matrix, determinant of that and taking square root of that. So what is that? Both are effectively the same. This one is meant for a non-square Jacobian in case of redundant robot like KUKA, AIVA and all, whereas for a 6 degrees of freedom robot, Jacobian is already a square matrix and you can directly use this. Okay, so for non-redundant robot, J is already a square matrix, WD and WM both are same. So this is the measure of dexterity. It measures whether the Jacobian is going singular or not. If it is going singular, as in case of fully stressed arm, so near to singular, it is no more dexterous. Okay. So the condition number is another similar measure. It is the ratio of maximum to minimum singular values of the matrix J and can measure singularity and other kinetostatic indices. So index is used to describe the dexterity of the robot. So this gives you a kind of value to compare the dexterity of a robot, and it is closeness of a pose to the singularity. Okay. So same robot at different place, because you know the Jacobian is varying. So at this position it will have a different dexterity measure than any other position where Jacobian is different. Okay. So the same robot can have different dexterity at different locations. Okay. So manipulability measure is the capacity to change the pose of the end effector of the robot, okay, at any given joint configuration. So let us say if you are fully stressed, you know you cannot do quite a lot of motions because it is already, the tip is fully aligned with the robot and it has extended fully. Okay. So it is a measure of how close again to the singularity. Okay. How close the robot is to the singularity. So that is what is manipulability. So a general derivation for velocity and force ellipsoid, which direction, how much force you can do. So that is what we will analyze here. Let us say you have a 2-DOF robot like this. Okay. So with joint angle, this is theta 1, this is theta 2. So at this position maybe it has some ellipsoid which is something like this, in which you can apply force. So ellipsoid basically the axis is, so the amount of force which it can apply at different directions. Okay. So these are forces. So this is the ellipsoid. So maybe over here it may have a circular shape. If it is fully extended, it gets fully collapsed. So you can apply only the forces, it is fully collapsed. Okay. So this is the case. Okay. So you see you have a varying shape of this ellipsoid ranging from a circle to fully collapsed, and maybe it looks like a circle over here. So this is what we want to analyze for the velocity and for the forces that it can deliver in different directions. So starting with this, so VE, that is the velocity, is equal to Jacobian times of theta dot. By the definition of Jacobian, you already know this. We have also derived tau is equal to J transpose of Fe. Fe is the end effector force. Jacobian transpose times of that would give me the joint torques. Okay. So let us analyze this, where V and Fe are has the dimension of m, that is the task space dimension, whereas theta dot and tau are n dimensions real number. So that is at the joint space, that is directly related to the degree of freedom of the robot. Jacobian will have m cross m dimension. If you draw along theta 1 dot and theta 2 dot, and the variables for that would be theta 1 dot and theta 2 dot. The unit circle equation for this would be theta dot transpose theta dot is equal to 1. So in case of theta 1, theta 2, theta 3, 3 variable system, so in that case it would be a hypersphere for n greater than 3. Okay. So for n greater than 3 it would be hypersphere, and for 3 degree of freedom it will be a sphere. Okay. So with this, now let us check this. So if you substitute theta dot from here, in case of velocity ellipsoid I want to find out, so it should be J inverse of VE would give me theta dot. So if I substitute that here, it becomes this. If I reduce it further, it becomes this, and further reducing it will give me this. So VE transpose JJ transpose inverse VE would become equal to 1. Okay. So this is equal to VE transpose A inverse this, where A is equal to JJ transpose. Okay. That is equal to M cross M. So this is now a square matrix. Okay. So in case of a generic value of velocity VE x, so this becomes this, that is any particular value if I put, so it is x transpose A inverse x is equal to 1. This is this symmetric and positive definite. So A is to be a symmetric and positive definite matrix. So the eigen values of A is lambda 1, lambda 2, lambda m, and eigen vectors will be v1, v2 up till vm. So if the matrix is m by m, it is like this. Okay, so this effectively equation x transpose A inverse x represents a three-dimensional space, represents an ellipsoid if it is a three-dimension one. So it is equal to v1, v2 and v3 are basically the eigenvectors. Lambda 1, lambda 2, lambda 3 are the lengths of these ellipsoids. So these lengths. So lambda 1 root over is the axes of the ellipsoid. So lambda 2 square root, lambda 3 square root. This is a mathematical representation. Okay, this is from mathematics, you can directly get it. Okay, so this is equation of ellipsoid as such, where eigenvectors and eigenvalues, they represent the direction of the axes and the magnitude of those axes. Okay, so what you see here is if A is this, then x is Fe. So in case you started with the equation with velocity V is equal to J transpose of theta dot. So in case you start with the velocity Jacobian, so in that case what you get is the velocities along each direction. Okay, so force ellipsoid is resulting from the unit sphere of joint forces and torques. So if A is equal to JJ transpose inverse when x is equal to Fe, it gives a force ellipsoid resulting from the unit sphere of joint forces and torques. Okay. So you see here, if you start with this, okay, VE is equal to J theta dot, so in that case this gives you a velocity ellipsoid. But if you start with this Jacobian, okay, so if you start from here, this also gives you a force Jacobian. In that case this becomes a force Jacobian. Okay, so this can either be a force on each side and it becomes a force Jacobian, and in that case it gives you a force ellipsoid. But if you start with this, with the unit circle as I have shown here, I got what is a unit circle of one radius and it is a velocity ellipsoid. Okay, so manipulability and force ellipsoid. So this is known as a manipulability ellipsoid when it is with velocity, and in case of force I commence with, so it is known as a force ellipsoid that I get. So manipulability ellipsoid, a circular shape would mean that end effector is equally manipulable in all the direction. Okay, equally manipulable in all the direction. It defines the end effector motion capabilities and captures how close the robot is to the singularity. Then what is force ellipsoid? It is same principal axes. So principal axis of this and this would remain the same. Okay, the principal axis lengths are reciprocal to each other. Okay, so both of these, if it is like this, the force ellipsoid would be like this. So that is orthogonal to each other also. Okay, the force ellipsoid has major axis orthogonal to the manipulability ellipsoid. Okay, so let me just vanish for a moment so that you can see it. Okay, now look at the velocity and force ellipsoid, that is known as the kinetostatic duality. In case of a 2R arm, end effector velocity ellipsoid would look like this. So you see, you have in this case, okay, this is the velocity ellipsoid. Okay, ellipse in case of a 2R planar arm, it becomes an ellipse. So you see, you can apply more velocity along this and less along this direction. So when it is configured like this, it is like this, and in this case when it is fully stressed, it is singular. In this case you can only move along this direction. So you see, your velocity ellipse is fully collapsed. Okay, you cannot move along this direction at all. And same in case of the force ellipsoid, you see, you can apply forces along this and this direction only, and this reduces to minimum. You cannot apply forces more along these directions. It is fully collapsed once again. Okay, the velocity one was something like this, the force one is like this. Okay, so you see, over here you can apply more force and less force, and in this configuration it becomes like this. So you see, the force ellipse and the velocity ellipse are orthogonal to each other also. So there are many other measures for manipulability. Measure 1 is the ratio of the longest to the shortest axis. So it can directly be derived from the velocity ellipsoid maximum and the minimum axis sizes. Okay, so lambda max, lambda min with square root. So these are the dimensions of those axes, should be greater than 1 normally. Next is, if mu is equal to 1, it is isotropic. It is equally manipulable in all the direction. In that case, lambda max and lambda min both are becoming equal and it becomes a circle or a sphere. Okay, a higher value would mean the robot is more close to singularity. Okay, so lambda max goes very high as compared to lambda min. So in that case it is near to singularity. So manipulability measure 2 is a condition number, mu square, it is nothing but square of this. So these all researches were reported differently in different times. So they look similar, but they were originated, defined from different people of interest. Okay, so it is mu square is equal to this, that is known as a condition number. This again is a measure how close it is to the singularity. Manipulability measure 3 is proportional to the volume of the ellipsoid. So volume of the ellipsoid mathematically can be given as square root of lambda 1, lambda 2, lambda 3 and so on, all the lambdas. It is square root of a determinant or this. So this is the volume of the ellipsoid. So higher is the volume, better it is. So that is, best one is the sphere. Okay, if it is fully collapsed, then it has a least volume and it is least manipulable. Okay, maximum volume occurs when the axes are equal and it is sphere. The robot can move with equal velocity in all the direction. Okay, same is true for force ellipsoid also. If the ellipse is becoming a sphere, that means it is able to apply, it can apply forces equally along all the directions. Okay, if the volume of the ellipsoid becomes large, the volume of force ellipsoid becomes small and vice versa. Okay, so it is like this. Okay, so the Jacobian normally is having two components, j omega and jv. In case of a 6-DOF robot, each of them is 3 cross 3, 3 cross n, 3 cross n. Okay, so overall Jacobian is normally 6 cross n, and it can be written as j omega is equal to 3 cross n, that is angular velocity and moment ellipsoid we can find out using this, and jv will give linear velocity and force ellipsoids. So, using j omega you can get velocity, angular velocity and moment ellipsoid. With jv you can get linear velocity and force ellipsoids. Okay. So, that is all for this lecture. In the next lecture we will discuss all the models that we have learnt in this week. So, we will compile them all together and we will try to create mathematical model. We will try to put them in MATLAB Simscape and we will try to simulate them all. Okay. That is all for this lecture. Thanks a lot.